There's a really good architect who was there doing, hash joints and optimization and hash joints at Oracle in 2003-4. And it was legendary that Larry actually gave him a spot bonus of $100,000 or something for making joins like 10 times faster.
Yeah.
Because these were early years, of, very large scale databases and big memory and things like that. So we're back.
Yeah.
And what a break. Change of scenery, change of background, change of clothes. We were in the midst of discussing the history, the last 50 years of machine intelligence and what we call artificial intelligence now. But we promised we'll come after the break. And this is what the break looks like. It's beautiful, isn't it?
Yeah. I love the tree behind us.
It's majestic.
Yeah.
And in many ways, nature is... I was reading an article about how nature is not just soothing, but also great for company building. So we do a lot of our offsites in places that are just extremely deep and rich in nature. Something for you to probably keep in mind as you think about simplifying things and bringing people together.
Yeah.
So we were talking a lot about, how things evolved. We were looking at the 50s, the 60s. We went to neural networks, to recurrent neural networks. We're talking about context. We're talking about memory. We're talking about, just the evolution of matrices in the process and going from, SIMD architectures and how you could take simple instructions, but, fairly powerful data structures like matrices and really get things going. The notion of an assembly line and how you could have simple tasks for lots of workers, and how that has been somewhat revolutionary in the way you think about things. Fewer managers, more developers in some sense, right? 'Cause that's one of the things that comes up in organizational building as well. And you had started making a case for how these things have actually really helped with, things like image processing, for example, RNNs and CNNs. Maybe we could take a step back and go back to the 2010s. And give a little view of what was going on in and around the Toronto area, Waterloo, Toronto, ImageNets. So what was going on? And then we'll get to, Google Translate, what was going on with natural language understanding, with translation and so on. But let's start there. Let's start with 2010s and Toronto and Waterloo.
Yeah, so the two sort of themes of progress around neural nets has been language understanding and image and video understanding. And both fields had their own bag of tricks, but there were a core group of people who really believed in neural net, who've been trying different techniques all along through the late 90s, through the 2000s, and trying different things. And one of the key things that people were trying to get was good vector representation of text or good vector representation of image. So that goes back to I think 1987 paper of LSI latent semantic indexing, when what some researchers did was said that you can represent a document as a very wide vector, right? So every word in that document.
And when you say wide, you're talking about 1,024 dimensions, or how many dimensions are we talking about?
So first we're going to talk about the sparse vectors, which means that every word in your vocabulary gets a position in the vector. So let's say that you care about most important 50,000 words in English dictionary, and so you have a vector that's 50,000 wide, and each position represents how many times that word was there in the document. So if you said the 30 times, then, and let's say position of the is 0, so you'll have a 30 in the 0th index. And let's say you said vector 2 times, and vector has a position 5,972, so there'll be a 2 over there. So that's the sparse representation of a document, right? And the thing with sparse representation is that you're using too much space to represent that doesn't have that much information. So you could look at compressing it in a way that it doesn't lose much meaning. So the first attempt was essentially use linear algebra to do this. So I don't know if you remember this principal component analysis thing, where what you're trying to do is take a very high dimensional vector and then just come up with some linear transformation to get it into a smaller space.
I'm smiling because one of my favorite data structures is Bloom filters.
Yeah.
And in fact, developers chuckle at it because I talk about that a lot.
Yeah.
Like, did we think of a Bloom filter here?
Yeah.
Because there's so much power in such a simple data structure, which it's probably the first probabilistic data structure that I used in my life. And it takes me back to Oracle 2003. There's a really good architect who was there doing, hash joins and optimization and hash joins at Oracle in 2003-4. And it was legendary that Larry actually gave him a spot bonus of $100,000 or something for making joins like 10 times faster. Because these were early years, of, very large scale databases and big memory and things like that. Linux was just coming on the horizon. And this architect's name was Mark Callahan. He went on to do MySQL, now MariaDB, was at Meta for a long time. And so I'm a big fan of his, just because, legend goes back that he actually improved hash joins 10x because of using Bloom filters for the first time within Oracle. What is the sort of overlap between what you were talking about in terms of taking these sort of bitmap vectors or whatever, counting vectors and bringing it through probabilistic hashing techniques to collisions and things like that? Like, was there any overlap? Was there any lessons learned from Bloom filters to this?
So I think a very similar idea. Bloom filters are using essentially hashing to compress the space, and so there's a lot of collision in there.
But at least it answers a question, which is it's not in deterministically.
Whereas when you're doing dimensionality reduction, you're approximating in a different way. You're trying to find a hyperplane through this high dimensional space that's closest to all the points in this hyperspace. So imagine in 3 dimension, we've got a bunch of points, right? And these points represent something, words, let's say. And there's no way to fit a plane through these points because they are not collinear, right? But just like we do in linear regression, if we try to find the plane that most closely approximates so that the square distance from the plane is reduced.
So we try to find neighborhoods and clusters?
Kind of, yeah. I think the better analogy would be like finding a line through the points, like linear regression. So linear regression...
I see. You're talking about just fitting a curve in some sense.
Yeah. So in this... So linear regression is essentially saying that I've got points in 2 dimension, and I want a single dimensional line that goes closest to it, right?
Absolutely.
So now imagine if you
and the reason why we're trying to find a line is so that we get a new input, we can predict the output with this approximation. And if you just take it to n dimensions, it's just an n-dimensional plane in some sense, a hyperplane.
Yeah, but the other way to think about this also is that now to represent a point, you just need 1 number instead of 2 numbers, because you could just say that along this line from the origin, what's the distance? Right? So once you encode the slope and the offset of the line, then you just need 1 number to represent every point. You would be approximating the point because you would be pushing it to the closest point on the line. So now imagine doing this in 60,000 or 50,000 wide space and coming down to, let's say, 1,000 dimension space. But the math is the same. It's essentially very deterministic linear transformation. And so you could go from sparse vectors to dense vectors through this linear transformation and go back over there. In process, you lose a little bit of information. But by doing that, each component of this 1,000-dimension vector essentially represents a conceptual topic. So like Coke and Pepsi will end up being same because they co-occur with the same
Soda,
set of words.
yeah. Like soda is going to be the neighborhood in which they'll all come together. So
yeah.
there'll be a dimension which is about drinks or soda in which they'll all come together.
Yeah. And so this was considered important for information retrieval when you're solving search problems. This was considered important for matching topicality. Like, for example, you're taking an ad about soda and trying to match it to a query that the user is doing about drinks to buy for a party or something like that.
So this was what was going on in and around Toronto.
Yeah. So this LSI was done, I think, in 1987 by a different set of researchers, but they were constrained with just linear functions because they're just using plain linear algebra. Now, if you want to introduce some nonlinearity into it so that you're not fitting a straight hyperplane, you can fit a manifold that's kind of regular, then that's when neural nets come in because they give you a good way of introducing nonlinearity. So a lot of people were trying to figure out if there's a way to take the sparse vector of words and turn that into like 1,000-dimensional, 512-dimensional space where somehow the space encodes meaning. So if 2 points are close together, they mean the same thing. And so that was one thing. And this is where this idea of autoencoder comes in, right? So you take this very wide vector, you feed it into a neural net with very wide input, and then it kind of progressively shrinks the dimensionality of the vector in each layer and goes down to whatever dimension you want. And then you start expanding back again, back to the original dimensionality. And then you don't need any labeling data. What you're saying is that I'm going to feed this vector in, and this
feed the vector in or feed any natural language input in?
So you take the natural language input, and then you turn that into a sparse vector, which 50,000 dimensions, something like that, right? And then you give it to this network, and its job is to sort of compress it down in the middle.
Essential number of dimensions.
And then expand back up.
To see what the loss looked like.
Yeah. And so all you're doing is saying, when I feed this vector, I should get exactly the same vector at the other end. And if I'm not getting, then I can backprop the error. And you do that with a lot of documents. And in the end, you end up reducing the error to something small. And so then you tap in the middle, and that's your embedding.
Got it. Yeah, I mean, and this is something that we also do in linear regression. So this is just in n dimensions. So it's much more of an n-dimensional problem than just 2 dimensions.
And some of the early discoveries which made people chuckle was that if you took the vector for king and subtracted the vector for man, add the vector for woman, you got something that was very close to the vector for queen. And so this was like, you can do arithmetic in conceptual space that was like unheard of.
So the word embedding is obviously an important word.
Yeah.
And it probably seems to have had its roots in 1987 paper, you're saying.
Yeah.
How did it start getting reused or reinvoked in 2010s?
Yeah, so I think the notion of, at that time it was called semantic indexing, and eventually it got called embedding, was around, but getting higher and higher quality embedding was one of the challenges that the neural net researchers were following. So that was one. And then the other one was image understanding. Right? So I give you a picture of a cat. Can you say that it's a cat through a neural network? And so that was the other thing going on.
Got it.
Yeah.
And what about Google Translate? Like what was the real phenomenon movement going on with consumer mobile devices and Google Translate? Were they also leveraging embeddings in some sense?
Yeah, so
autoencoders?
Yeah, so Google Translate is very interesting, another thread. So a long time back, when linguists were trying to come up with a way to translate, it was all rule-based, right? So this is my grammar in this language, this is my grammar in this language, this is how this word translates, so go look up in the dictionary and try to do it. And of course, that doesn't work very well because it's not that straightforward rule-based thing. There's so much context going on. So the early versions of Google Translate was essentially statistical translation in the sense that you take a sequence of words, like sequence of 3 words or 5 words, and then look at the translations and see if there's a sequence of 3-word or 2-word over there that maps to this. And if you find lots and lots of instances of these 3 words here co-occur with these 2 words here, then you just build a pairing.
Mm-hmm.
And when you try and translate something, you find the longest sequence of words for which you have a pairing in your rule book, and then you just replace it with that.
Mm-hmm.
And then you do a little bit of smoothing.
Clearly an unscalable problem because of so many of these n-grams that you can find, and it's still rule-based, you were saying.
So it was statistical, as in nobody was putting in rules.
Mm-hmm.
They were just looking at like translated books, translated transcripts of news and things like that. So there was a body of data that said this thing translates into this thing.
Sure.
And it was just statistically trying to find the longest n-gram, like sequence of n words from here to here. And obviously it with n, it grows exponentially.
Mm-hmm.
So you were only looking at the most frequently occurring n-gram combination. So for 1 word, you'll have translation for everything, but for 2 words, you won't have every pair, but the commonly occurring ones, and so on for 3-word and 4-word.
But you would still call it rule-based? Because it was a data structure that was fairly linear.
Yeah.
Interesting. And did they then say, let's just take both languages and map them to embeddings and see what's close by?
Yeah. So this is where neural nets started playing a role. And I think this was actually a little bit later than 2010. So maybe we should talk about what happened in 2010-2012. This is the time when there was a little bit of resurgence and excitement around neural nets. And I remember I was at Google and Andrew Ng was there, and I was doing the machine learning models for predicting ads. And Andrew Ng and Jeff Dean were trying to start Google Brain. And so they had started from this autoencoder problem, and they were talking about how we can use these autoencoders to do better ad ranking and solve other problems at Google.
And by the way, they were doing all this without having much access to many GPUs back then.
Yeah. It was not GPUs back then. It was like Google style throwing a ton of CPU.
And what was the parallel programming paradigm of its time? Like whatever we try to leverage through GPUs now.
Yeah.
Were we just doing brute force map reduce on these things, or what was going on in terms of data flow architectures and parallel distributed programming frameworks?
Yeah, so I think initially it was MapReduce, and then there was some custom systems built just for this kind of
And that
learning.
what was the emergence of TensorFlow?
Yeah, so TensorFlow came out of that work a few years later. Initially, I remember there was a code base inside Google called autoencoder, and it was like very custom parallel programming.
I know it's a digression, but I still want to get to the 2 frameworks. The PyTorch framework and the TensorFlow framework. And I know they have converged now in some sense, with one being on top of the other. But somehow I feel like Facebook's or now Meta's frameworks become more popular than Google's framework. And I want to go back to AngularJS versus JavaScript or React.js, sorry. Both of them are JavaScript frameworks. There was Google's Angular, and then there was Facebook's React. Obviously, React took over. We know who the winner was of Facebook's framework. And a similar thing happened between TensorFlow and PyTorch. Maybe as a digression, I'd love for you to get into the why of why it happened. I have a point of view, but I'd like to hear from you.
Yeah, so this is a topic I've thought about and talked to a bunch of friends quite a bit. So I think before TensorFlow came out, there was nothing like that, right? And so Rajat and Jeff and Andrew were trying to figure out how to scale machine learning more and more. And then GPUs became popular, and Google started building its own hardware, and then it was apparent that it's very hard to ask machine learning researchers to think about CUDA and stuff like that, and it's much easier to give them a layer of abstraction where they can think of essentially in terms of the
Tensors.
tensors and networks and things like that. And so they came up with this idea of like, we'll give you a configuration language in a language that like a lot of people are familiar with, which is Python. And at the back end, it will configure a high performance C++ CUDA system to do that. And
it was CUDA even though the hardware was not GPUs and NVIDIA? Or the TPUs were actually, or maybe you're saying this is pre-TPUs.
So this is the time when a lot of machine learning switched from CPUs to GPUs and also TPUs in Google's case. And so once they switched from CPU to GPU, that's when I think TensorFlow became a need because most engineers didn't think in terms of CUDA. And so they needed a layer of abstraction. And it was not just that they needed a layer of abstraction on top of CUDA, but there was a set of concepts that, like, conceptually how you think about neural nets versus how it gets compiled down to machine code. There was a gap of abstraction in the middle. And then the other thing was also convenience, was this automatic computation of gradient. So if you use simple functions in your building blocks, you know what's the differential of those functions, right? And then you just have to multiply those partial derivatives to get the total gradient. So as a researcher, you don't have to think through that I compose these layers and how should I compute the gradient for each layer. It's kind of, once you define the network, it's relatively straightforward to figure out what the gradient should be.
So they probably layered more higher level abstractions.
They layered.
And these were like training and inference abstractions of neural networks rather than matrix multiplication, the kind of stuff that NVIDIA was known for or CUDA was known for and so on. But what happened between PyTorch and TensorFlow?
Yes. So, like in programming, there's this builder paradigm where, like, sometimes when you're doing something complex, you take a data structure and you call a bunch of builder methods to build compute graph or something like that. And then you say .run, and then it does everything, and then every time you get a piece of data, you run. So that was kind of how TensorFlow was. That, like, you do some mental gymnastic in your head to figure out, like, what structure do you need, and you call a bunch of functions to build this whole network, and then you kind of run through it. So it was a little bit lower abstraction to force the programmer into thinking that, like, how I'm architecting this graph. So instead of saying C is equal to A plus B, you will say builder.adder and sort of add.
Was it more Lisp-like, you think?
I don't know enough Lisp to be able to say.
But just the fact that the functions were actually also, just common variables and things like that in your... But I mean, because I go back to, maybe it's a distraction. I'll go back to what PyTorch was doing then. Like, how was it doing things differently than TensorFlow?
Yeah, so PyTorch came up with much simpler interface than TensorFlow for defining these things. Now, initially, PyTorch...
Was it more procedural?
Yeah, so if you want to add two things, you just say C equal to A plus B, as opposed to, like, thinking of building a network where there's input coming from here, input coming from here, and there's an adder here, and so on and so forth, right? So the syntax was more convenient, but the underlying implementation was slower, initially at least.
Just like it was with PHP.
And,
I mean, you can look at Rust versus JavaScript, for example, It looks like there is something to be said about Meta's culture of building things that are simpler, even though they might be slower, versus Google's culture of machines are faster, but humans probably are slower. Is there a dichotomy of that nature that you've seen between the two companies?
Maybe so. So Google's culture, at least back when I was there, was really all about, like, low latency, high performance coding.
But also
and,
machines are faster.
Yeah.
And we'll figure out humans. And, especially at scale, 100,000 humans. Whether they need to actually have simpler abstractions or not is a thing that's punted for the future or something.
Yeah, like, I mean, as Google engineers, we took pride in knowing sort of these low-level details and being able to manipulate it and squeeze the last amount of juice from compute, like this famous Jeff Dean's presentation about like numbers every engineer should know, like what's the latency of a single instruction and like what's the latency of...
By the way, I like those.
Yeah,
I like those a lot. In fact, we used to do that at Oracle too.
Yeah.
Every instruction mattered. I mean, it takes me back in time, but we used to be proud about VTune, this Intel's thing that would tell you about number of instructions and number of loads in stores and all that. But I think it built a great culture of every penny matters, every cent matters, every instruction matters and such, Maybe coming back to this idea of embeddings, because, even at our company right now at DevRev, it's the biggest pivot for all our developers. Because, last 30 years, we got really lazy with rules. And now we have to think about models. And when I say models, I mean adjacency thinking, similarity thinking. I mean, all these problems that we see business managers do, which is classify and cluster and deduplicate and triage. Triage is a bunch of all these things, right? When you sit... Product managers and support people sit, they're triaging, but what are they really doing? They're labeling, they're deduplicating, they're deflecting, they're routing, they're classifying, they're clustering. All these ings that I just said right now is basically what we're expecting of AI now. So what is it that humans do that machines have to do better? I think it comes down to similarity thinking. And the biggest data structure that every developer has to think about is n-dimensional vectors. If you can map every concept, every log, every alert, every ticket subject line, every ticket description, every developer skill to embeddings, now we have done all these verbs in way simpler ways than before, I mean, to shun rules is the hardest thing in business software. Right? Hardest thing. I mean, I can tell you that the last 5-7 years of conversational AI, whatever intercoms of the world used to call conversational AI, was not AI. It was just rules. Bot builders and decision trees and the things would just break because they had happy path assumptions about what text to assume and things like that. So, I mean, I can tell you that the biggest transition or the biggest elevation at DevRev right now is to have every developer think about embeddings. It's such a core data structure, and it's visual thinking. It's immensely visual to think about n-dimensional and thinking and to take every abstraction you have into the world of vectors.
So you're taking like these tickets and workflows and mapping them into vector space and then using that for categorization and
I mean, like basically
deduplication.
There's so much junk sort of entities in every business database. 10 to 15 to 30 copies of the same thing or similar things. Wrong assignments to people, wrong assignment of parts, which is components and things like that. And nobody has cared up until now. So we do all this fancy analytics downstream, but the upstream stuff is garbage. Right? One has to be really meticulous about not just the text, but also the metadata that goes and the fields that we assume are so high quality or very low quality. But I think the biggest challenge and opportunity in business software is reduction. So how do you do reductive things? How do you cluster them? How do you classify them? How do you route them? How do you attribute them? I mean, to know that we have to route something to a support agent or to a support engineer or to a developer is really mapping their skills, the day-to-day skills, that their repos, their check-ins and all this stuff to a recent outage of a microservice. I mean, a microservice outage and how it ties back to a repo and what was checked in the last 3 days ago, to me, is a embeddings problem.
Very
right?
cool.
I mean, thinking about space, which is a microservice is in a certain neighborhood, but the GitHub repo and the check-ins of the last several days are also in a certain neighborhood. So how these things are close enough that I can do at least speculative debugging is a big problem. I mean, incident management, for example, is a space-time search. So we are spending a lot of time on embeddings. And just like MapReduce was cultural, parallel thinking was cultural, distributed thinking was cultural, because it was so easy to build monolithic systems where you assume one big box. And now you have to think about distributing across n machines. And like, okay, so who's going to bring it together? Like, well, that's where MapReduce comes in maybe. Or I think it's a very similar challenge and opportunity. We have thought about rules. We assume that, rules are things that one could actually just bring together into a single large database and stuff like that. To going into model thinking is one of the opportunities of a lifetime for any business software company. But then more than that, I think it's also customizing these embeddings, which is where it becomes enterprise business software, not just business software for SMBs, but enterprise business software, because they bring in their own dimensions.
Yeah.
See, I think the challenge of building enterprise business software is, can you collaborate and co-create value with people outside your company? Because otherwise you're building a black box. It's hard to configure, customize, extend. And I think what happens with successful business software companies that they say, look, we are willing to collaborate and co-create value with our customers and the partners who are implementing these things for our customers, or the developers who work for these partners and customers. And that's why, we have customized the heck out of everything in dev, all the way from the object model to the security model, authorization, authentication, but to event models, to SQL, to now I think AI models. Obviously, one could switch LLMs, but the question is, if you had embeddings and you thought that these were the right embeddings, but they wanted to put it in 3 more dimensions. Like, why would they want to put 3 more dimensions? Is because they want to do context-aware search. If there's a search agent, let's say an AI chatbot that's sitting on their app, and there's a user that's coming from this country versus that country. Now, how you actually do deflection of their questions could be based on that context. So there's a dimension which is their location that needs to be put in. And in the past, call center workers would pick up the phone. They were trained to say, ask them the country where they're coming from. And then based on that, look in this folder. And a folder was basically a cluster. It was a rule-based cluster. And there was a rule-based routing, and there was a context coming in, and you would actually go look up that folder, let's say for KYC documents, because a KYC document for this country is different than a KYC document for this other country. Or for a product user of this product A versus a user of this product B. They had completely different knowledge-based articles to look at. So we had figured out rule-based mechanisms to take context and basically segment and isolate them into different folders where the knowledge-based articles were kept. Now we got to do all of this stuff in a completely autonomous, automated way, where you don't have folders, but you have clusters of documents. So how you take this human thinking of folders and map it into this model and machines thinking of clusters with so much distance between 2 clusters that there's no way this country's user actually were to be shown a KYC article of this other country is at the core of a lot of our thinking. Like, go from folders, i.e. strict structures, rule-based structures, to clusters, and over time you might add more dimensions to it. Like today they might ask with country, tomorrow they might actually put a zip code or an IP address or a product ID and things like that. So how do you make this customizable? Where this data structure you thought was n dimensions was really n plus 3 dimensions is the final bastion in our overall customizable enterprise business software. Because then you can do, as I said, context-aware search and things like that. And, the more things change, the more they remain the same. I'm a big fan of that. The cookie is not dead. I feel like the cookie lives. Like, now the cookie sits inside the chatbot. Right? Because you are willing to take the location of that chatbot and actually bring it in as an abstract data structure that you can then use as the n plus first dimension or the n plus second dimension to build a new embedding along the way is just as relevant today as it was before. So at the core of every modern business software, people say is AI, but when you try to double click and triple click what it really means, if you don't have great embeddings thinking within your developer base, and you're not able to customize it, then you're not building enterprise business software. So I'm very passionate about embeddings. So I'm glad you actually brought it up.
Very
the idea of embeddings, and I think the way we can reduce the amount of work for managers is where machines get really good at thinking semantic, similarities and adjacencies and things like that. So now we go from embeddings to 2017. Maybe that's a good transition, you think?
Yeah.
Because it looks like we've been hyping up 2017. I wonder what else happened in 2017. I'm trying to think of beyond the paper that we'll talk about. What else happened in 2017? Do you remember anything?
What else happened in 2017? I guess
I can tell you one thing that happened. This is just off the cuff, but we had a soft quarter in 2017. And this was our second quarter after going public. And a lot of learnings about planning, by the way, which we'll get to. I think at one of the episodes we have talked about is next token versus Q learning and planning backwards and things like that. How do you work backwards? I think we should just dedicate one episode to planning and working backwards and how humans and John Doerr and everything that actually this was Amazon and the culture of working backwards is no different than what we are struggling with in AI as well, which is working backwards. But 2017 looks like a seminal year for and I'm going to call it brute force, but maybe it was not brute force hardware thinking. But going from RNNs and CNNs to attention. Say more about attention is all you need and what really went on with that paper.
So there's actually a bunch of very interesting ideas that all came together, and these were not necessarily new ideas. Some of them were, but it was the first instance when a group of people made it work in a very meaningful way, right? So the idea of attention is that, so if you look at sort of a regular neural network, what's happening is that your inputs are getting multiplied by fixed weights and then getting added. That's the matrix multiplication bit. And then it's going through a nonlinear function. And
so say that again, just slowly.
So your inputs are getting multiplied by weights. These are the learned weights. And then getting added.
And this is all happening at each node of a neural network. So that you know which neuron to actually go after. So in some ways...
And
then you said you go through a function. So talk about that.
A nonlinear function. So the most popular nonlinear function these days is ReLU, which is kind of like... So for every negative value, it gives you 0. And for every positive value, it gives you the identity. So it kind of goes like this and this. So it just goes... That's the bit that introduces nonlinearity. If you don't have that, then you could collapse all the layers into just matrix multiplication one after the other, and you'll get essentially a product of all the matrices as a single matrix. But because you're introducing these nonlinear things, you cannot collapse it, and that's what gives you the ability to craft different...
One thing I'll encourage, if you look here, you'll go slow for the audience. There'll be more empathy for the audience. What he just said, say that one more time. Because I think our audience is also business people, and, as you know, product managers and people like that as well. Entrepreneurs who are trying to figure out how to hire good architects and product managers. So last 2 minutes, maybe if you slow down a little bit.
So I said you multiply things and then you add things, right? And that's on the individual numbers in the vectors. In some ways, you could think of matrix multiplication as taking points in n-dimensional space and then rotating it and scaling it. So every matrix multiplication is essentially rotating the axes and then scaling.
And I'm doing all this because I need to make a decision in the neural net of which next neuron to get to.
Maybe so. So let me try this analogy. So let's say that I have a bunch of points here that represents, I don't know, a customer that's going to churn, and a bunch of points here in this space that represents a customer that's going to expand, right? And so the dimensions could be like how much usage there is.
Yep.
Dimensions
Could be like 10 good dimensions.
Yeah, how responsive they are and things like that. But I know roughly like these points here are bad, these points here are good.
So I'm trying to find a hyperplane that differentiates the two.
Yeah, so I'm going to find this plane in the middle that differentiates the two. So how do I do that? So I can, let's say this is my x-axis, this is my y-axis, this is my z-axis. I can turn this axis parallel to this plane, and then I can sort of shift this axis over here, right? And then I can say everything below 0 of my x-axis is bad, and everything above is good, right?
Got it.
So you're taking these three axes and turning this, and then shifting it over here, and now you know.
Yep.
Right? So every matrix multiplication is essentially an act of rotating the axes and then
moving the axis.
Yeah, scaling it, right? Now, if you do a bunch of rotations, one after the other, you can represent it as one rotation, right? Because I rotated this by 30 degrees, I rotated this by 30 degrees, and so on. But at the end of the day, it can all be represented as single rotation, right? But when you introduce these nonlinear functions, you're essentially squashing the space in some ways, right? So now when I rotate and then I squash the space, the next rotation cannot be combined with the previous rotation because now the structure of the space is completely changed. And so the more layers you add, the more complex this function gets, and it can no longer be seen as like single rotation. And what that means is that it gives you the ability to construct this manifold or sort of curved hyperplane to separate these things, and you're no longer limited to like a linear hyperplane. You can have a bunch of bends in there.
Got it. And why did it matter in 2017? We were going back to the attention paper itself.
Yes. So what I was saying was that if you look at these operations, there is never a multiplicative effect between one input and the other input in this kind of multi-layer perceptron architecture, MLP architecture, right? You're always just sort of linearly adding these things, some multiplication and then adding these things. So one input is not going to control the other input's contribution to the output.
They're orthogonal.
Yeah. So because the operations are essentially addition between two inputs. There's multiplication, but that's with fixed weights. If I introduce multiplication in here, where I take this input and multiply this input with it and take the output, that's a different kind of function, right? And it's not that this idea wasn't there, but like previous attempts at doing these kinds of multiplicative networks didn't produce good results.
Physically, mathematically, is this like a dot product of two things that we are doing here? And what does a dot product deliver? Like if they're close enough, then will they reinforce each other? And if they're far enough, will they diverge? Is that what's happening physically about dot products of two vectors? I've been trying to understand why dot products are such a basic fundamental operation in this idea of relevance, similarity, adjacency context. And physically what I have come to at least understand in my simplistic sort of brain is if they're close enough, they'll reinforce each other. If they're far enough, they'll diverge. Is there any truth to that?
Yeah. So let's say that you and I, we want to know how similar to each other are. So let's say one of the dimensions is where we grew up. And so we grew up pretty close, same state in India. So you multiply these two things and you get a high number. And if, let's say, some dimension along which we are different, like the car you drive and the car I drive, now you take the dot product and the product is going to be low because they're different, and you add these things all up, and
So
kind
by
of
the way,
gives you
that's a
similarities.
very important piece for the audience too, because let's say I have two vectors, 1, 0, 0 and 0, 1, 0.
Yeah.
If we do the dot product, I'm going to get 0, 0, 0, which means that the third thing is further away because these two didn't agree on any one dimension.
Yeah. Yeah.
I mean, the 0 of this basically pulled the other one down as well.
Yeah. Yeah.
Is that a good way of thinking about dot products?
Yeah. Yeah. Yeah.
And the closer they are, like if I have a 1 in both of them, they reinforce each other in that sense, right?
Yeah.
And therefore, I understand similarity better based on if they vehemently agreed in their dimensions, they're going to reinforce each other in that sense.
Yeah.
Is that a fundamental thing that everybody listening to should understand about dot products?
Yeah.
I'm feeling good about myself now. Like you reinforce a little bit of, like I'm not that dumb, you know. In the way I try to think about things more physically, and visually I'm like, okay, they're actually reinforcing each other, they're pulling each other apart and diverging from each other.
You have a very good way of explaining complex ideas.
No, because to myself I'm like, okay, I am dumb, I'm slow actually, I'm very slow. If anything, with age I'm slowing down even more in the way I think. By the way, should we move a little bit this side just so that you're not getting the sun? I know you don't put sunscreen. I'm going to move. Yeah, I think we're fine. Yeah. So, dot products.
Yeah.
Then what?
Yeah. So, here. So, the idea of attention existed before self-attention. And the idea of attention came from the fact that when you're translating from one language to the other, you are going to pay attention to different words at different positions, right? So the verb might come in the beginning in one language and might come in the end in the other language. And when you're producing the word corresponding to verb in the end, you need to pay attention to the verb that came in the beginning in the other language. So somehow your network needs to know that now I need to pay attention to the embedding for this word over here. And when I move to this other place, I need to pay attention to this one. Okay? And so some of the researchers thought that, why don't we train a network that will tell me which word to pay attention to during translation? And so this mechanism was called attention. And this was also kind of the first place where we were multiplying inputs together as opposed to adding them. And so that gave a greater degree of freedom for the network to learn new kinds of things.
So what is the physical relationship between dot products and attention? I know we went through it a little bit. But the word he in a second sentence, where the first sentence talked about George W. Bush. I am trying to figure out if he needs to attend to George W. Bush. And somehow I do some dot product magic to actually say they're actually related.
So think about it this way, that imagine if there was a rule book somewhere that said when you're thinking about understanding he, you need to pay attention to George Bush. And the way it did that was by giving you a number for each word, which was 0 for every other word and 1 for George and Bush, right? Or maybe you've combined George Bush into a single entity and there's a 1 there. So now what you could do is you could multiply the embedding with this corresponding vector and add them together, right? So let's say the sentence was George Bush was president. So for George Bush, the vector is 1. For was, it's 0. President, it's 0, and so on and so forth, right? And so when you multiply the embeddings and add them up, you essentially get the embedding for George Bush.
In this case, the dimension on which they're agreeing is the fact that they're both subjects as opposed to objects or verbs. Is that where they're coming together? And that's why the dot product actually converges?
Yes, something like that. So I peel the onion one layer. Let's now peel to the second layer. So now I have this essentially this weighted vector that's saying the weight of George Bush is 1 and everything else is 0 when I am decoding he. Right? Where do we get this weight vector from? So in some ways, what we're training the network to say is that he is going so the network that's representing he is going to announce that I am looking for subject, and it does that by producing a key vector, and then each of these words are announcing what are the properties that I have. So these are sort of value vectors coming out of different attention heads. So one of the value vectors coming out of attention head is going to say that I am a subject, right? And so the key is saying I'm looking for a subject.
Is that a key or a query? Because I thought there was a QK.
Yeah. So,
right?
Sorry. Yeah. Query. Yeah, query. So the query vector is saying that I'm looking for a subject, and the value one is saying that I'm the subject. And so when you take the dot product of these two things, you get a high value. Everywhere else, you get a low value. And so you've taken dot products of these things, and then you've multiplied that with embedding, and then you added it up. And result of all of this is that now the embedding for George Bush is available for decoding he. And so then you combine these things again, and you get a better embedding representation for he.
Got it. So what was the seminal breakthrough in the paper? And I remember once passed, you were talking about an activator network as well, or let's just say more about what happens in a node. You're doing some dot products now between the inputs, but then you also have this look-aside network, a smaller one.
Yeah.
What was that introduction, and why was it introduced? Was it for the prompt and the fact that a prompt was acting as an influencer in this? And
so if you look at, we were talking about vanishing and exploding gradient problem in RNN, right? So what's the solution to vanishing and exploding gradient is that you short circuit the long chain with a shorter chain, right? So even if the words are 100 words apart in the text, can I have a short circuit connection from here to there, right? Now the problem with that is that now every word is talking to every word, and so the size of the network grows quadratically, right? And this was one of the key realizations that the team that came up with transformers had, was that, hey, I don't have to keep looking infinitely back. As long as so the initial attempt was up to like 4,000 tokens, right? So if I'm just creating a network between every word to every word within a 4,000 word network, it is quadratic, but we can deal with it. It's going to be large, but we can deal with it. And so they said,
because that fit into some GPU hardware memory or something?
Yeah. So now you have connections going from 4,000 to 4,000. So you've got essentially 16 million.
And that is what a matrix would represent in some sense, right?
Yeah.
Because the connects are basically a squarish matrix or something, right?
Yeah.
Okay.
So this became the attention network. Now, so the first level idea is that we are going to limit the context not to infinite, like in RNN, but to a fixed context, and then that allows us to go quadratic, and that solves the vanishing and exploding gradient problem by limiting the context and allowing a lot more parameters.
More connectivity.
Now, this connectivity, what's the nature of this connectivity? The nature of this connectivity is this attention mechanism. So the attention mechanism is essentially each word generating a query, and each word also generating a key, and then you multiplying them, and then you're adding the values, and so that allowed you to statistically learn that in this situation, when the input is like this, I should be paying attention here. Right? And then the other interesting idea that was introduced was positional encoding. So in this network, if you look at it topologically, there's no difference between things that are 2 words apart versus things that are 5 words apart, and so on and so forth. And so they introduced a way of encoding position of each word as yet another vector in there. And then you do this multiple layers, And so over time, a lot of sort of context gets disambiguated.
Got it. And obviously, GPUs were coming on the horizon. I think they were getting cheaper because of gaming and crypto.
Yeah.
So they realized that you could actually get an open system, which is not TPUs only. Did that have a role to play? Because obviously what Google was building in TPUs was very custom hardware.
Yeah.
And on the other hand, what Facebook was trying to do was more with NVIDIA, I guess, even back in 2017.
Yeah.
And something happened there where maybe the crypto and the gaming worlds commoditized or subsidized AI in some sense. Was there any correlation with that at all?
So I think GPUs were already quite popular even before crypto wave started.
Gaming, I mean, sure, we would talk about gaming, and the mobile world probably had some sort of image work going on and so on, which is, I mean, it was kludgy to begin with. I don't think Google Photos, it was okay what they were trying to do, but they were trying to do it in their own cloud.
Yeah.
Was there anything happening with mobile devices in terms of image recognition? I know that Apple probably does a good enough job of face recognition now.
Yeah.
But does that happen on the device, or was it happening in Apple iCloud?
I think Apple has stuff on the device itself.
So obviously there was all this work going on in GPUs and hardware, which probably helped make this a little bit more, I would say, general purpose than TPUs and what Google was trying to do. I mean, when did NVIDIA and how did these things converge? 2017 paper, the access to hardware. I mean, you talked once about brute force too, which is what this 4,000 times 4,000 thing is, brute force.
Yeah.
Was there anything that, I mean, of course, OpenAI was doing some things with that paper then. And then what happened? I don't know. I'm trying to figure out if COVID had a role to play in this 2020, 2021. Like, how did 2022 happen? Because December 2022 is when you look back and say Big Bang. Obviously, it was brewing for like 5 years or 6 years before that.
So there was this other idea that people had talked about for a long time, which is the idea of transfer learning. So you and I know a lot about the physics of the world, and that helps us. Let's say we are playing a video game. We don't need that much input to learn the different physics of a video game, because we can transfer a lot of learning that we have from just existing in the real world. And so people were talking about this for a long time, that to do any task, I need to build a classifier, sentiment analysis, or I need to predict the next word. Why do we have to solve these things from scratch every time? Whereas as humans, we leverage this knowledge built from learning other tasks. So can't we just have like one Uber model that learns a lot of different things for different tasks, and then it can generalize across the tasks? So this idea of transfer learning was being talked about, but there weren't that many successful instances. And even as this 2017 paper comes along, it's just purely talking about translation, nothing else. So it pushed the translation benchmark quite a bit, and that made a lot of researchers look at it. But for general people, it was nothing. Like no one really paid attention to it.
That's no pun intended.
Yeah. and then two things happened. So almost in parallel. So at Google, a bunch of NLP researchers come out with BERT.
But that was 2014 or?
No. So that was based on Transformer. So I don't know, 2018, 2019, something like that. So BERT was really the big breakthrough that made everyone look at it. Because what BERT was doing was that...
Did BERT exist before that?
No, BERT is based on transformer architecture. So,
Interesting.
So T in BERT is transformer. So what they did was they used the transformer architecture to predict any word in a sentence by... So they said, like, I'll give you the whole passage, but I'll delete one word from it. And then the network has to guess what that word is. And they use the transformer architecture for that. But along with that, they also created an embedding vector for that passage of text from the same network. And they use that embedding to predict if this sentence follows this other sentence. So they'll take a passage of text and say, these two sentences are right next to each other. So in that case, if I give you the vector for this and vector for this, you should produce one. And if I pick two random sentences from somewhere, then the output should be 0. And so this forced the network to learn an embedding for sentence from the same underlying representations. And then they use this vector to do all kinds of NLP tasks. So classification, sentiment analysis, like predicting answers to questions and things like that. And it moved the benchmark for several NLP tasks simultaneously using same network. And that was the big breakthrough. That's when a lot of people started paying attention to transformers.
And this was the GPT 2.0 or?
So along the same lines, so BERT was very complex objective function and doing a bunch of different things. GPT-1 came around the same time.
In parallel.
Yeah. And GPT-1 was just saying that I'm just going to predict the next word. And
this is what the OpenAI guys delivered then.
Yeah.
So out of the transform paper, there's two things going on. One was what Google was working with BERT on.
Yeah.
And were they encumbered by TPUs in some sense?
So,
because it was not at scale. These were still 20, 30 million parameter models at best, maybe 70 million parameter models versus a billion and 10 billion and 20 and 100 billion.
Yeah.
Was that because of access to clusters and big clusters of NVIDIA GPUs versus small TPUs?
So this is where I think it's just a question of precedence. So no one else had trained such large networks, right? So BERT in its time was really, really large, like an order of magnitude larger than...
But did it have to do with, like the way, I look at Yahoo versus Google.
Yeah.
One of them just hadn't built distributed systems with commodity hardware big enough to really do map reduce.
Yeah.
Right? The other one just said, look, we're going to do GFS and all this stuff. But it was an approach to hardware which is commodity.
Yeah.
An approach to open source software which is commodity.
Yeah.
Was there some level of commodity things going on in OpenAI compared to Google?
So I don't think OpenAI has any scale advantage over Google.
Even though one of them was using Google hardware versus using NVIDIA clusters?
Yeah. Like Google has enough NVIDIA there as well. And it will...
Was there a not invented here back in 2018-19? Because they were so committed to TPUs. Remember, they were committed to TensorFlow and TPUs.
Yeah.
Versus the outside world, I think even Meta included. They're like, no, I think the world has moved on to PyTorch and, you do training on NVIDIA and things like that. I'm still trying to figure out if they didn't build large enough things because they were not commodity enough in their thinking.
So I think a different problem happened at Google. This could have been a problem, but this wasn't the problem. A very different problem happened at Google. So after BERT, people got super excited. And GPT-1 came around. It didn't create as much buzz as BERT because BERT was really the one that beat a whole bunch of benchmarks. And the folks at OpenAI said that, like, I don't need to complicate the network. I don't need to complicate the objective function. I'm just going to scale this thing a lot. And at the same time, Google did too. And what was happening was that initially, these networks were just learning the pattern of language from internet, and there was a lot of toxic language there. So it would say a few intelligent things, but it'll also say a lot of just batshit crazy stuff. And for Google, this was beginning to be a problem. Legal problem, a reputation problem.
Sure.
And then there's a particular researcher who complained about it, and it became a political issue.
A bias issue that came up as well. So you're saying obviously it was a big ship versus a small agile ship, boat or something, and then OpenAI was just an agile boat.
Yeah, so Google went the direction of, okay, we are going to research on all this in private, and we'll see where it goes. There were internal people at Google pushing very hard to say, like, we should have a chatbot interface. There was a There was a chatbot inside Google called Mina, which was equally good, but the powers to be didn't want to expose it because they were afraid that, like, what if it says something bad about King of Thailand and our entire Thailand business is shut down and things like that.
It's the innovator's dilemma. In many ways, there was a revenue to be protected.
Yeah, but what happened at OpenAI was both sides knew that there was an alignment problem, that you need to align this network with human values. But this is where RLHF got invented at OpenAI, and they
took it to an emerging economy, and they got a ton of labeling done that way.
Yeah.
Which was brute force.
Yeah, I think there was innovation in there. It's not sort of a very interesting theoretical innovation, but there was innovation in there that caused these things to be a lot less toxic and usable, and that kind of exposed the power that these networks had.
It's fascinating what you just said about big ships versus small boats.
Yeah.
I think this is probably an episode already.
Yeah.
I know that we covered a lot of ground with respect to embeddings and attention. And then finally, when you said something about labeling and the fact that sometimes you have to use brute force, human labeling, to really make something palatable. And for a startup to do this, where both Microsoft and Google, at least Microsoft said, look, we'll do this arm's length. We don't have to worry about lawyers and Congress and all sorts of social value issues and media and all that. Let the startup take care of it. Probably was a big reason for this thing to really make progress. And then 2022 happens. Obviously, a big reason for that was the consumer grade version of ChatGPT in some sense. Even school kids using it for homework and stuff. So we should probably put a bow on this episode now. What's your last word on what we carried through the last hour plus? And what is the one takeaway that viewers should take from this episode?
So there was a very interesting lecture I was listening to recently, where I think this was a researcher from OpenAI. What he was saying was that we've always kind of, when building intelligent systems, we've thought about how we think and then try to design a machine to follow our thinking and automate that thinking. And that was all the classic research where people were trying to build systems with symbolic logic and things like that. And over time, what happens is that when the amount of compute... So what this does is that it constrains the way you learn, right? And when you have less compute, that's the only option that will work. If you make it too unconstrained, then it's not going to work. As more and more compute gets available, you have to go away from the way we think our thought process goes and our logical reasoning, our brain works, and just throw more compute and data at the problem. But it's not like just throw data and compute and no constraints and things will work. You have to have the right amount of constraints at the right time. So at this time, this much compute is available, this much data is available, so this much constraining of the problem is needed. And so at every point in time, you have to figure out what's the right amount of constraints. And as compute and data increases, those sort of hand-designed networks and hand-designed constraints and objective functions kind of become less and less relevant. And so over time, probably we're going to see that it's just going to be about a lot more data and
a lot more compute.
That's
a great sort of way to summarize. I was chuckling when you were talking about this because Yuval Harari in the book Sapiens, he talks about why Homo sapiens happened. Because there were obviously other Homo Neanderthals and obviously Denisovans and all these other, and sapiens happened. And his conjecture is very similar to what you just said. Talks about the discovery of fire, which could be GPUs in our case, for all we know. He talks about how before fire, our intestines were longer because raw meat took that much long to get digested. And really there's two core sinks of energy in a body. There's the gut and there's the brain. That's it. These are the two places where are the biggest sinks of energy. And obviously when we had raw meat, the more of the energy actually started to go here. It's something that we see with food coma when you actually eat and then go back.
Yeah.
It's like so much energy goes
Yeah.
into the gut. And then he said fire happened. And then all of a sudden there was cooked meat.
Yeah.
And his conjecture is that the gut, human gut, started to shrink because it didn't need to be as long. So more and more and more of the energy started going to the brain. Hence Homo sapiens.
Yeah.
I'm like, this could be what you just said about throwing more, compute and throwing more data at the problem. The brain has to get bigger.
Yeah.
And that's the only way you actually get to, and maybe controlling fire was that sort of big black swan moment in the world of Homo sapiens.
Yeah.
With that, it's been a great episode, Amit. Thanks again for the nth time explaining to me everything that I thought. And it's great to actually go back to the basics of even things like dot products and linear algebra and hyperplanes and things like that. Always a student. Thank you.
Thank you.
Yeah.
Thanks
Awesome.
for doing this with me.